Myself, Sonia, I am discussing with you a topic. Hydrolysis of a salt when water is dissociated to a very small extent into H positive or OH negative ions. H2O gives H positive or OH negative ions. In pure water, the concentration of H positive ions and the OH negative ions are equal to each other. Pure water is completely neutralized. Salt of strong electrolyte, when dissolved in water, they dissociate almost completely in the positively charged ions or the negatively charged ions. In some of the salt, the ions of the salt react with H positive ions furnished by the water, therefore lowering the concentration of H positive ions in the solution. Since the product of concentration of H positive or the OH negative ions is constant, then the concentration of the solution of H positive OH negative ions in the solution increases, becomes alkaline. In the case of some other salt, the cations of the salt react with OH negative ions furnished by the water, therefore lowering the concentration of OH negative ions in solution. Kw is constant. The concentration of H positive ions in the solution increases, so the solution becomes more acidic. The phenomena of interaction of ions and the cations of the salt with the H positive or the OH negative ions furnished by water, yielding the acidic or the alkaline solution, is known as the salt hydrolysis. Hydrolysis may also be considered as the reverse of neutralization. Neutralization, as we know, that involves combination of H positive or the OH negative ions yielding undissociated waters. It involves most complete in disappearance of H positive or OH negative ions. Hydrolysis, on the other hand, leads to the information H positive or OH negative ions. Salt of strong acid or the strong base. Salt of strong acid or the strong base do not hydrolyze. Consider, for example, potassium chloride. When it is dissolved in water, its ions H positive or the Cl negative has no tendency to react with H positive or OH negative ions of water. This is because the possible product of such interaction, namely KOH and the KCl, themselves almost completely dissociate. Salt of weak acid or the strong base. Salt of this category undergo hydrolyzed to gives the alkaline solution. Consider sodium acetate is an example of this category. When dissolved in water, it undergo almost completely dissociate into the Na positive or the acetate ions. Sodium acetate gives us acetate ions or the sodium ions. The undissociated water further dissociate so as to maintain the constant value of Kw is equal to concentration of H positive into concentration of OH negative. The H positive ions again take up by the acetate ions, and this lead to an increase in the concentration of hydroxyl ions, decrease in the concentration of hydrogen ions. The solution becomes alkaline. The aqueous solution of the salt of a weak acid or the strong base is alkaline because of hydrolysis. Hydrolysis constant. The hydrolytic reaction of sodium acetate may be written acetate ions or the sodium ions plus water gives us acetic acid Na positive OH negative. Sodium ions is common on both sides of the equation. It may be left out and the equation may be represented. Applying the law of chemical equilibrium and taking the concentration of water as a constant. Relationship between KH and KW, it should be noted that ultimately when the equilibrium of hydrolytic reaction of sodium acetate is established, the following two equilibria has been satisfied. Acetic acid gives us acetate ions or H positive ions. Water gives us H positive or OH negatives. Gives us the following equation should also hold good. K is the dissociation constant of the acid, and K is the Kw is the hydrolysis constant. KH is equal to KH is equal to Kw by of Ka. The hydrolyzed constant KH of the salt varies inversely as the dissociation constant Ka of the weak acid. Weaker the acid, greater is the hydrolyzed constant of the salt. Degree of hydrolyzed. Let's see moles per liter be the initial concentration of sodium acetate in the aqueous solution. Let X be the degree of hydrolyzed, which is defined as the fraction of the total salt that has undergo hydrolysis on the attainment of equilibrium. If X is the small as compared to unity in the above equation may be replaced by the 1 KH is equal to CX square, or X is equal to under root of KH divided by of C. By meaning it is impossible to calculate the degree of hydrolysis of a salt of a weak acid or a strong base at any concentration C of the salt, provided the dissociation constant K of the acid. pH of the hydrolyzed salt solution. In the hydrolysis of sodium acetate, OH negative concentration is equal to Cx. Substituting the value of X, concentration of OH negative is equal to C into raised to under root of Kw divided by of Kc. Taking negative logarithm on both sides, pH plus of POH gives us 14. pH is equal to 14 minus half of pKw plus half of log C plus half of pKa. Salt of weak acid and the strong base. Consider ammonium chloride as an example of this category of salt. In water, it undergo almost complete dissociation into Na positive or Cl negative ions. The ammonium ions take up hydronium ions furnished by the water to form dissociated base ammonium hydroxide. The undissociated water further dissociate so as to maintain the constant value of Kw. This cause an increase in the concentration of hydrogen ions and a decrease in the concentration of hydroxyl ions. The solution becomes acidic. An aqueous solution of the salt of a weak base or a strong acid is acidic because of hydrolyzed constant. The hydrolytic reaction of ammonium chloride may be written as, since chloride ions is common on both sides of the equation, it may be left out and the equation may be represented as applying the law of chemical equilibrium. KH already mentioned is known as the hydrolyzed constant. Relationship between KH, KB or the KW. KH is equal to Kw by of Kb. It is evident that the weaker the base, the greater is the hydrolyzed constant of the salt. Degree of hydrolysis. If C is the initial concentration of the salt in moles per liter, X is the degree of hydrolysis on the attainment of equilibrium, then the concentration of the various species. Then KH is equal to Cx square, then X is equal to under root of KH by of C is equal to under root of Kw divided by of Kb into C. As in the previous case, the degree of hydrolysis of a salt at a given temperature is more if the base is weak. That is, if Kb is smaller, and X increases when concentration decreases when the dilution increases, since Kw increases much more with temperature than Kb. Degree of hydrolysis at a given concentration increase with rise in the temperature. Salt of weak acid and the weak base. Salt of this category may be explained by the ammonium acetate, the ammonium ion and the acetate ions furnished by the salt combination with OH negative or the H negative ions of water to form dissociative hydronium ions or the acetic acid. It is represented as, in this reaction, both H positive or OH negative ions are removed simultaneously. If they are removed in equivalent amount as in the present easy, the solution remains neutral, although hydrolyze of the salt has been taken. The equilibrium law equation for the hydrolyze constant in the present case written as the following. Other equilibria also exist in the solution according to law of chemical equilibrium. K is equal to this, Kb is equal to this, and Kw is equal to this. By substituting into this equation, Kw divided by of Ka into Kb. Thus in this case Kh is equal to Kw divided by K into of Kb. The initial concentration of the salt is C moles per liter and X is the degree of hydrolysis. Then at the equilibrium point the concentration of the various species may be shown. Kh is equal to X square. X is equal to root of Kh is equal to under root of Kw divided by Ka into of Kb. It is evidence from that the weaker the acid and the base, greater is the degree of hydrolysis of the salt. It should be noted that in the case of degree of hydrolysis is independent of the concentration of the solution. Kw increase with temperature much more rapidly. Either Ka or the Kb degree of hydrolysis is increased with rise of temperature. pH of the hydrolyzed salt. K is equal to concentration of H positive or the acetate ion divided by the acid. pH is equal to 1 by of Kw plus 1 by of Pk minus of Pkb. If Pk and the Pkb are equal, then the pH is equal to half of Pkw is equal to 7. The solution is neutral in spite of the fact that the extent of hydrolysis may be considered.